In this screencast, we continue our exploration of average rate of change. Let's look at example 5.2. The table below shows annual carbon dioxide emissions for the world during the period from 1980 to 2009. This data was taken from the World Bank. In this example, the letter T is going to represent the independent, or the input variable, and the letter W is going to represent the dependent, or the output variable. In part A, let's calculate the average rate of change, delta W over delta T. This is the same as what we've calculated previously. It's the change in the output, so in this case the change in the emissions, divided by the change in T, the change in the input, which in this case is the change in time. Let's go ahead and write our answer in scientific notation as well, and we'll be sure to give units for our answer. So let's go ahead and calculate this ratio. First of all, in the denominator, we calculate the change in time. In going from the year 1980 to the year 2009, the change in time, in other words, the time elapsed, was 29 years. The numerator is the change in the emissions. If we take the final amount, that's the 3.21 times 10 to the 7th, and we subtract the original amount, 1.95 times 10 to the 7th, and this is kilotons, which I'm going to abbreviate with KT. This is what we need to calculate. Now, one tip. In the numerator, notice that we are subtracting two quantities, both of which have powers of 10, the same exact power of 10 in them. When that happens, a simple way of performing the subtraction is to simply subtract these two numbers by themselves, the 3.21 and the 1.95. Go ahead and subtract them first and then multiply your answer by the 10 to the 7. So in other words, I'm going to take 3.21 minus 1.95. I'll calculate that subtraction, I'll multiply by 10 to the 7th, and that's how I'll work out my numerator. And this is, again, kilotons. The denominator, again, is 29 years. So when I perform the subtraction in the numerator, I arrive at 1.26 times 10 to the 7 kilotons divided by 29 years. And now I'm going to go ahead and divide the 1.29 by the 29, and then I'll multiply my answer by the 10 to the 7. When I do that, I arrive at 0.043 times 10 to the 7th, so that's my final value, and the units are kilotons per year. Now, we want to give our answer using scientific notation, which means we need to rewrite this value as 4.3. So we need to have that decimal point moved over between the 4 and the 3. If you actually calculated the whole quantity, so with the 10 to the 7, you would move the decimal point 7 places over to the right. So if you actually wrote out what this number is as its full decimal, what you would see is if you took 4.3 and multiplied by 10 to the 5th, it's exactly the same number. So I can rewrite this as 4.3 times 10 to the 5th. And this is kilotons per year. Now let's go ahead and look at part B. So here we're going to explain in practical terms what the ratio we just calculated is telling us in terms of how the annual emissions are changing over time? Well, if we look at this quantity, it's a per year quantity. So, and this quantity is positive. So, for each year that passes, the annual emissions must be increasing by 4.3 times 10 to the 5th kilotons. Now remember, we learned in our previous screencast that this increase, this yearly increase, may not be the actual increase in every year, but rather it's an average yearly increase. Again, think back to how this number was calculated. We took the total increase in emissions over this time period and we divided. If you divide the total change in the emissions by this 29-year period, what you're getting is the average yearly change in the emissions. So let's go ahead and write this up. So in the period 1980 to 2009, emissions for the world increased by an average of 4.3 times 10 to the 5th, and this is kilotons, per year. How big is 4.3 times 10 to the 5th kilotons? Well, if you go and you write this out in its full decimal form, you find that this is 430,000 kilotons. So this is to help you have some perspective as you think about what that number means. Let's go ahead and look at the next example. So in this example, there's no context. We're not talking about emissions, we're not talking about time. In this example, we have a function, and we're assuming the function is given by this equation. So the letter x is playing the role of the input, the letter y is playing the role of the output, f is the name of this function. In A, we're asking to determine the average rate of change of this function. In other words, delta y over delta x. Change in output divided by change in input, and we want to do it for this range in input values. So we're going to calculate the average amount that the output changes every time you increase x by 1 unit. So let's go ahead and do this. A good way to start these calculations is by making a table of values first. We did this in previous examples. So I have x and I have y, input and output. Now we are interested in the range from 0 to 3 in x. So what we want to do now is calculate the corresponding output values for these two inputs. This is where we go back to our function. If I replace x with my two different inputs, I can arrive at my outputs. If I substitute 0 in for x, I get 0 for y. If I substitute 3 in for x, I get 9 for y. So from this table, we can see that the change in x, if I think of going from 0 to 3, the change in x is 3. In other words, 3 minus 0. And the change in y, again, that's the final value minus the starting value. That change is 9. and we want to calculate the ratio, which would be the change in y over the change in x. So 9 divided by 3, which is 3. Part B. Now let's explain what the ratio delta y over delta x is saying about the outputs of this function and how they are changing. Well, to help you understand how you can interpret this ratio, let's write it slightly differently. So I'll do this here. So we calculated delta y over delta x, and we arrived at a value of 3. I'm going to go ahead and write this as 3 over 1. So the denominator in this fraction still represents a change in x, and the numerator still represents a change in y. So in particular, we have a change in x of 1 and a change in y of 3. So our input variable has increased by 1 unit, and our output variable has increased by 3 units. So this ratio is telling us that whenever x increases by 1 unit, y, the dependent variable, should increase by an average of 3 units. Remember, that word average is important here because we don't know if y really always increases by 3 units. It may just be an average. Now this increase in x by 1 unit, this is as long as x stays within the range 0 to 3 that we were given in the last part. So let's go ahead and write this down. So within the range 0 is less than or equal to x is less than or equal to 3. So within that range, whenever x increases by 1 unit, the output y increases by an average of 3 units. Now let's go ahead and look at part C. Below is a graph of the function f in this example. Using only the graph, determine which of the following is larger: the average rate of change over this range or the average rate of change over this range. So let's figure this out. First, let's talk about the average rate of change over this interval. This is actually what we calculated in part A, but let's go through it one more time. So in this range, to find the average rate of change, again, we would probably start with a table of values like this. We would get our table of values from looking at the graph. We are interested in the range from 0 to 3, so they form our starting and our ending values for x, and to get our starting and ending values for y, we go to the graph. So when x is 0, notice that we are at this point right here, and when x is 3, we're at this point right here. So notice that when x is 0, you can see that y is also 0, and when x is 3, y is 9. Again, we saw this from part A. So the average rate of change delta y over delta x is the change in y, which we calculated to be 9, divided by the change in x, which we found to be 3, and of course there was our answer of 3. Now let's go and look at the other range, from -2 to 3. Again, let's make a table of values to start us off. Our starting value is -2 and our ending value is 3. We know that when the input is 3, the output is 9. We've already seen that. When x is -2, we can see that we're at this point on the graph and our output is actually 4, so y is 4. Now let's go and calculate the change in output divided by the change in input. Remember that you take the ending value minus the starting value. So we'll take the 3 and subtract the -2. 3 take away -2. And then in the numerator we take the 9 and subtract the 4. So we arrive at 5 in the numerator and 5 in the denominator, which gives us a result of 1. So now let's go back and answer the question. Using only the graph, determine which of the following is larger: the rate of change over this range or the rate of change over this range. Well, you can see 3, of course, is bigger than 1, so the average rate of change over this interval is larger. So we'll write that down. So the average rate of change over 0 to 3 is larger.